Hi, thanks, Daniel. Okay, I'm going to change track a bit. I'm going to talk about a platform that we're building at SICS for data science. I'm not going to go into prediction models. And I'm going to talk a bit about a Hadoop platform we're building for, we've been building for a number of years. Now, you may have heard of Hadoop. If you haven't, you've kind of probably missed a bit on the big data scene. But in case you didn't know and you don't read Hacker News, Hadoop isn't the cool kid anymore out there. So you may have heard of Apache Flink this morning and Apache Spark and some other platforms. But Hadoop as a platform is kind of losing a bit of its edge. So what we're doing with our platform was we're trying to make Hadoop great again, as the Donald would say. So keep your message simple. That's what I've been told. Okay. So you may not know what Hadoop is, so I'll just tell you briefly. So Hadoop is really, you may have heard of cloud computing, and you have different cloud computing platforms, Microsoft's, Amazon's, Google's, and then you may have your own on-premise cluster. But what Hadoop adds to it is you have a resource management framework, and you have storage capabilities, and the cloud platforms have their own resource management frameworks and their own storage capabilities. And then you have a lot of data processing frameworks at the very top. Now, some of you who work with data science may be familiar with TensorFlow, you may be familiar with R, you may be familiar with Python, and they run on Spark, the platform. And you can do programming up here to work with massive volumes of data that are stored down here on these platforms. So typically what people see as Hadoop is this narrow stack in the middle that you're going to run on your own premise, you're going to run with the Hadoop file system, with Yarn, and you're going to have a couple of frameworks that come along with it. And some of these other data processing frameworks at the top, like Spark and TensorFlow and Kafka and Flink, they're not really part of Hadoop as people see it. So we don't look at it that way. Here's our particular Hadoop platform. We even have TensorFlow up there. We've been actually working this week with students on a course I'm giving on large-scale machine learning and deep learning, and we're running TensorFlow on top of data stored in Hadoop. And that's a relatively new feature that's out there. We have a platform running up in Luleå where SICS have a data center, and we have about 54 machines running this entire stack there. If anyone wants to try it out, I'll give you the reference later on, but it's pretty much open for all researchers and even industry here in Sweden. So what Hadoop typically does is it simplifies all of these services. Nobody wants to go in and install every one of these services individually. You want to have somebody come along, maybe somebody like Hortonworks or Cloudera, and say, here's our tool, Cloudera Manager. You can install whatever bits you want. And we have our own version of that, so you can install this platform in a few clicks. But that's really kind of what you can think of being Hadoop ecosystem as being. You have large volumes of data. Maybe it's in the cloud, maybe it's not. We'll do some processing. Maybe it'll be with tools like Spark or Flink, or maybe it'll be TensorFlow. But really, you know, how do I get this as one unit that I can just kind of work with? I can put my data in this big data platform and then process it either in TensorFlow or Spark or whatever. So I'm going to talk a little bit about our storage layer. And if you've gone to the cloud, you'll be familiar with this concept of things called object stores. So if you're going to go to Amazon Web Services, they'll use S3 as your object store. If you're going to go to Google, you'll have Google Cloud Storage, and Azure, Windows Azure have their own Windows Storage service. And they provide a storage service called object stores. Object stores are not as good as hierarchical distributed file systems, period, right? You may read and say, well, you know, it's a store. I can list the contents of my bucket in S3. I can insert into it. I can read from it. It's a false equivalence, right? They provide different semantics, different behaviors. What that means is that if I have an application, and I can give the example of Spotify or Netflix, who and even Databricks, who write the Spark platform or manage it, what they've had to do is rewrite their applications, because if you do things like, for example, read an object that you've updated in S3, when you try and read it, you mightn't get the object you updated. So you don't have read-your-writes consistency semantics. If you're working in Google Cloud and you insert an object into a directory and you list the contents, you might not see that object in there. So we have these what we call eventual consistency semantics because of the way they're built. They're built to scale better, but the cost is that the behavior you see as an application developer isn't as good as you get in a strongly consistent hierarchical file system. And you won't get the, the hierarchical name system properties like quotas, permissions, and other things. So just to make this a bit more concrete, Netflix developed a whole framework called Semper, and Semper was to get around problems they had in a lot of their applications that they build. So they build these workflows which will maybe parse some data, write to S3, and that will kick off another job which will read from S3. And oh, whoops, the data isn't there. I know it's there because the first job finished and inserted it, but the second job hasn't seen it here. Now, if you're an application developer, you'll know that that means you have to do something. You have to say, okay, am I going to wait and poll and see if this thing has happened? How long do I wait for? Your code becomes very complex. You need to have timeouts. Are they going to be exponential timeouts? Netflix decided, okay, let's just implement a whole new key value store, which kind of is a mirror of what we think is in S3. So any object that we actually insert to S3, we're going to tell our other key value store that we've inserted this to S3. So we're not going to trust S3 to say if the data is there. We're going to go and look in our key store first. Google had to do Spotify had to do the same thing going to Google Cloud. They've tried porting that Semper application, but they're using their own one now. Now, you may say, well, why don't Amazon do something about this? Why don't they open up S3 and let us know what's in there, what the metadata is? Is the object being copied? Do we see it anywhere? They don't do that. It's basically a Pandora's box, and they're not going to open it for you. And the bottom line of this is that if you write eventually consistent applications, they're hard. It's much harder to write them than it is to write applications for strongly consistent file systems or databases for that matter. Now, I'm going to make a prediction, and it's based on some of the work we've done, but it's based on what we've seen in databases in the last few years. So in databases, they didn't scale to this big data cloud scale 10, 15 years ago. So what happened was we saw a movement of NoSQL systems. So NoSQL systems are databases, but they don't give you necessarily ACID guarantees for your operations on the database. So they're weakening the guarantees you get when you insert or read or write data to your database. What happened was that NoSQL databases became popular. People found them very difficult to use. And there's a vanguard of companies, for example, Google have a database called Spanner, where they've said, hang on, we can get both the scalability and the strong consistency semantics in one system. And there's a whole new area called NoSQL databases that scale to very large sizes, but they provide you with ACID guarantees for their operations. So we've seen that move in databases from ACID guarantees on a single server, go distributed, we weaken them, and then eventually we strengthen them again and we get a nicer system. So we haven't seen that in file systems yet. We've gone from a single data center file system like the Hadoop file system. When you go to multiple data centers or cloud, now it's just object stores. I think we're going to go back there again. And the reason I'm saying this is because of what we've done at SICS and KDH. So we've developed a distributed hierarchical file system called HopsFS, which is really just a re-architecting of the Hadoop file system, the metadata layer in particular for it. And we've seen that we can scale it by a factor of at least 16. So we're getting at least 16 times the throughput of it. And what we did as an original problem was we looked at this hierarchical distributed file system that Hadoop has, and it has a single server that has to manage all the metadata for the system. So what we said was, okay, this is a problem. We're going to try and move that metadata off this single server, which is actually just on the heap of a single Java virtual machine, limited to about 150 gigs, 200 gigs. And we moved it into an in-memory distributed, one of these new SQL databases, developed right here in Kista as well, actually called MySQL Cluster or NDB. So we did that, and this is what we got. We got over 1 million ops per second on Spotify's Hadoop workload. So this red line you see at the bottom here, this is the performance on Apache Hadoop, and this is with the single metadata server. And as we add metadata servers and database nodes, we just scale. And we reached a limit basically on the number of machines we had up in Luleå at our data center. I think we ran with 70 machines or something like that. So we got up to over 1.2 million. I'm pretty confident we can go higher than that. And that's throughput. So that's telling us how many operations per second our file system can handle. What about the capacity of it? What if I wanted a file system that spanned an entire data center with 50,000 servers? Well, yes, we can do that too, because our distributed database, you can go to 12, 24 terabytes. without too much difficulty. And this little blue line here is what the 200 gigabyte kind of limit that Apache HDFS goes to. So the way we did it was that we took this single server and replaced it with a set of stateless servers called Namenodes. And then this is our distributed database. And we can independently add servers here. So we can independently scale it out online. And we can also independently add nodes to the database online. And we've done the same thing with Yarn, which I haven't talked about the figures for it, but we have some nice figures where we can see scalability up to about 25,000 servers as well. And we re-architected it a bit so that a lot of the traffic coming from the nodes that manage the compute talk to a set of stateless servers. So we offloaded that from the cluster scheduler that makes the decisions about what applications run where in the cluster. Now, you may say, okay, well, this isn't particularly interesting for me. I'm a data scientist. You know, what's in it for me? Well, we have metadata, right? So we have a lot of metadata capacity now. And what do you want to do with it? So we've added APIs to our file system. So you can take any file system object, a file, a directory, and add some arbitrary JSON to it. That JSON may have a schema, may not have a schema. You can go in and change the file system, the Hadoop file system, by adding tables to your database. So adding new features becomes much easier in this type of model. And the features that you add, we can make them much easier to add because the consistency of anything we add will be guaranteed by foreign keys in our database. So if I have a file represented by a table called inodes, and I want to add metadata to it, I can do that, and whenever I remove this inode, the foreign key will make sure that the metadata also goes. So the consistency of the metadata is guaranteed. And if you look at Hadoop and how it's going now, this is where they spend probably most of their programming effort, and many thousands of lines of code in the services provided by Hortonworks and Cloudera on platforms like Ranger and Sentry. So we like this thing called strongly consistent metadata. So if we have metadata in the same database as our metadata for our file system and for Yarn, we can maintain the integrity of it with transactions and foreign keys. Sometimes we can't. Sometimes we're using services like Elasticsearch or Kafka. The metadata is external to our database, so we have to use protocols to ensure that we synchronize the metadata. So for example, we export the entire namespace of our file system to Elasticsearch. So you can search HDFS in sub-second latency. And we do that with a platform called ePipe. Now, there is another type of metadata which is even worse, right? Because this type of metadata is nice. It's just one way. We're using asynchronous replication protocols. We may get some duplicates, but in general, it'll be consistent. But when you have metadata that is maintained at two different locations, like we have access control lists for Kafka in our database, and the metadata is also over here in Kafka and Zookeeper, we need to maintain the integrity of it by custom recovery logic and polling. And this is the kind of thing you want to keep away from. And this is what you have a lot of in the Hadoop platform. It's pretty messy. So the upshot is that we have this nice tinker-friendly metadata, and we can add new features easily, like erasure coding. We can add a new security model that we've added, free text search. And what's interesting for data scientists are the abstractions that we've added. So we've added a couple of new abstractions to Hadoop. So if you look at Hadoop and you've worked with Hadoop, Hadoop is users, applications, jobs, files. You create a new cluster if you've got sensitive data. You've got to work with ACLs, Kerberos. You have to ask sysadmins to do things for you. Our model is much simpler. We just simplify it down to this notion of projects. And projects are sandboxes where the only people who are users of it have access to it. The project may have data sets. Data sets can be shared between projects. And then we have Kafka topics, notebooks in Apache Zapple and jobs as well. So we're trying to simplify massively the Hadoop platform with new abstractions we've introduced because we have metadata. And this is kind of what it looks like as a whole. So I'll just kind of jump over this. We have our strongly consistent metadata here, and then the services that we're adding on outside of the Hadoop stack, like Kafka and Elasticsearch. The platform is running in production. We've been running for, since the middle of last year, or this year, up in Luleå, and we have quite a large cluster. We have about 150 or so users up there. I think the second phase is going ahead. This is a data center that SICS are running in Luleå. SICS North are running called SICS ICE. And we're providing Hadoop as a service there. It kind of looks like this. If you're to log in, you have a bunch of microservices here. It's completely UI driven. If you want to try it out, you can go to our website, hops.site, and register, and I'll approve an account there for you. But we have things like notebooks, Apache Zeppelin, free text search up here. You have data sets to manage. You can add members to your project. And it's very user-friendly and easy to get started in the Hadoop space. So just to summarize, what we're working on is a new version of Hadoop. It's called Hops Hadoop, and it is the only European distribution of Hadoop. What we've done is we've made it more scalable, more tinker-friendly. It's completely open source. And from our perspective, what's interesting is that we've made this huge leap forward in terms of the performance of HDFS, and hopefully we can bring it out to the cloud scale. So there's a lot of us working on it. Here's some of the names. I hope this is up to date because it changes every few weeks. And we've had a lot of master students and working on it, and now we have a core group of people working on it who are spread over SICS and KTH. And that's it then. So you can find out more about us here at our website or at the GitHub site. We have Gitter channel as well if you're interested. Then I'll take questions. Thanks.
And let's have a look at some questions. Yeah, you have one there, bottom right.
I have difficulty understanding that. When are HopsFS and NDB commodity? So commodity as in commodity hardware. This runs on commodity hardware, if that's the question. If they're all open source, so we have different licensing models. We have Apache v2 and GPL v2, but they're all open source. So has there been work on multiple languages, i.e. clustering and finding? No, that's not my own.
No.
Okay, do you plan to make an Apache project? We would be interested in doing that, I guess. We have some issues. I've talked to people at Apache Incubator. We have some issues related to the fact that it's a fork of Apache Hadoop. And some of the features we could include in Apache Hadoop, like the Yarn side, but the file system we couldn't. So we've been in discussion with them, and unfortunately, to make that leap, you have a lot of work to do, right? So we would have to re-implement our backend in Apache Derby, which is effort we're not spending right now. But we're interested in principle in doing it.
So now this is getting really difficult. But I think how does Hops integrate with Spark?
So it doesn't. So Spark is provided as a service from this UI. So you can go in to the user interface and you can run a Spark job as a compiled jar, or you can go to the notebook and write your Spark program in Python or in Scala, or R if you want. If that's your favorite. Yeah. Okay. I think we're done. I think.
Yeah.
Okay.
When can Hops generate artificial humor? No, that's
Hops. I don't know about that.
All right. So let's thank Jim again for his talk.
Thanks.